Well, welcome to a problem now, because here's a problem that is sometimes given in physics labs where they'll say, okay, well, from your understanding of projectile motion, let's see if you can make a steel ball fall into a cup. Okay, so let's draw a cup here. And let's say that cup has a height of 0.1 meter. Okay, so 10 centimeters. Now we have to sort of think about, okay, well, we need to know its range, its change in x, and its initial velocity in the x direction. Because if you think about it, our equation says that our change in x, that its range, is dependent upon the initial velocity in the x direction times the time of flight. Well, we know we can calculate the time of flight based on how high it is. So once we have the time of flight, we've still got two unknowns, change in x and change in x component of velocity. So I guess you can just then make a decision and go, okay, well, which one of those are we going to do? Because it depends on the question. If the question says, where do you place a cup to make it fall, then you're going to have to know this or calculate that, right? And so what you can do is you can go, okay, well, on our table, we're going to get a ruler and we're going to measure that and make that have 1 meter. And we're going to drop this ball, so we make a ramp, and we're going to drop the ball down the ramp so it travels along that 1 meter, and then we can calculate its exit velocity from the table. In other words, its x component. And if we can do that, we will have the x component, we'll have the time, and that'll give us the range, right? So that's what we might do. So first of all, let's calculate the time it takes of time of flight. And here's where we need to be a bit careful, because when we've got a cup, if this ball was to come down like this, it could hit the side of the cup. We want the ball, if we can, to come down and go into the cup. So really, it depends on where we're measuring our range. Are we measuring the range at the end of the cup, in the middle of the cup, or the front of the cup? If it's the front of the cup, it's probably going to hit the cup rim and smash the cup, right? If it's the back of the cup and the cup's heavy, the cup might stay in there. In the middle of the cup, it might just miss the rim and land in the middle, depending on how high the cup is. So we have to take into consideration the height of the cup. If we're taking consideration the height of the cup, then we can basically treat this problem as if it's landing in the middle of the cup, just about there. Okay, so we're going to do our change in height now, our change in y formula to find the time. So change in y is u y t plus a half g t squared. Now, of course, we know this is always equal to 0 because it's the same as if we just drop it. So we have change in y is equal to a half g t squared. Well, instead of change in y, how about we use the symbol h for height? Then we times both sides by 2, so 2h is equal to g t squared. Then therefore t squared is equal to 2h over g, and therefore t is equal to the square root of 2h over g. So this could be a formula that, if you like memorizing formulas, you could just memorize that one, okay, and use that rather than having to write this out of the time and substitute. But of course, every time you memorize something, you got the fear that you may forget it. So it's best to sort of derive it from the original equation. That way you know you're on the right track. And of course, this time of flight is for horizontal projectiles. When we start moving into parabolics and symmetrical parabolics and uneven or asymmetrical parabolics, then the equation changes. So you may as well just go from first principles. But that's what we're using pretty much now. Okay. So if we plug our values in, what do we get? Okay. Well, the change in y of the h here. All right, so change in y is equal to 1.2 minus 0.1, so 1.1 meters. And so 2 times 1.1 divided by g, 9.8. And when we do the calculation, it's 0.474 seconds. 0.474 seconds. That's the time of flight. So now we've got the time of flight, we're going to have to sort of calculate an exit velocity so that we can calculate the range and where to place the cup. Okay, so we've worked out the time of flight it's going to be. Now, depending upon the question that your lab group gets, you're going to have to work out your initial velocity in seeing how far you have to place this cup. So let's say you construct your 1 meter you construct the ramp and you don't let it hit the ground, you've got to catch it. So let's say you drop your ball, the ball travels on the 1 meter and then comes off here and you catch it, right? Catch it as it exits. And you time how long it takes for it to travel that 1 meter, right? So you're trying to calculate from a certain height its velocity. So velocity is equal to displacement divided by time. And well, displacement, I really should use S, shouldn't we? Okay, I was thinking of distance. So velocity is equal to displacement divided by time. We said the displacement is 1 meter. And you're going to time how long it takes when you do this in the lab, releasing it from a certain point, how long it takes to go that 1 meter. Then you'll have its velocity, its initial velocity, or you could just put U there for initial velocity. So let's say you time it 0.75 seconds. 1.3 repeater meters per second. So let's say that's your initial velocity, 1.3 meters per second from wherever you release it from. So now you know this, now you can calculate the range. So doing all that, it says that if you drop your steel ball from whatever height you had to get your initial velocity of 1.3 meters per second, and the time of flight is 0.474 seconds from that height, then you should be able to place your cup 0.63 or 63 centimeters and it should catch it. Now, of course, what are some of the assumptions here? Well, you're assuming that there is no loss of energy here, which there is, but we'll see how we go. There's frictional energy being lost there. And so our calculations here are rough-ish. Okay, we released it from a ramp to increase its velocity, and you are going to lose some of it here, but depending upon how you construct it, it may or may not be a lot. And then, of course, the conditions of the air, it's going to get a very small distance to travel, so air resistance is going to be negligible anyway, unless you're doing it right near like a wind tunnel. So that's sort of how you can sort of problem solve out how you might go about doing this. And then you can do other experiments, such as how does the height from which you drop the ball affect the range? And so you're testing the variables there, the independent variable being the one is the heights that you change, the dependent variable is the range. So you can do investigations like that. Hopefully that sort of gets your brain cells thinking about possibilities and gets you to generate more questions and keep exploring physics, and I'll see you in the next video when we do more great physics stuff. See you then.